Hello everyone. Today our group, Crispy Deep Fried Tempura, is going to present you cardiac mapping system as a final project for EGBI 330 Biomedical Measurement and Instrument Subject. These are the members of our group. These are what we are going to cover for today. You can see here in the slide. Let's start with the introduction. Cardiac mapping system is a system used to treat cardiac arrhythmia. It is an irregular heartbeat caused by improper electrical signal within the heart. The way to treat it, we have to insert the catheter and reach the heart chamber. First, we use mapping catheter to map electrical activity within the heart, and then we find abnormal tissue or atrial fibrillation, and we treat them using ablation catheter. These are what our catheters look like. Mapping catheter and ablation catheter here are going to control by the main system. And we also have localization, which is a system used to locate the catheter while it is in our body, and EKG sensor to see the heart activity. All of the systems are controlled by Raspberry Pi 4 here, and it will send the information and represent in the user interface, and physician can see it all the time. Next is catheterization, or the way to insert catheter to the heart chamber.
For catheterization, the Agilist NXT steerable introducer from Abbott Company is applied because of the ability to approach hard-to-reach area. The fluoroscopic and echocardiographic guidance is used during the catheterization to navigate the activity. The introducer is inserted through the guide wire to the right atrium by accessing the femoral vein and leading the catheter to the cardiac. In case of the need to access the left chamber, the Transseptal puncture technique needs to be applied, using the Transseptal needle for piercing through the septum to reach the left atrium. And next is the mapping part.
For mapping catheter, there are 5 main components, which are controller, tip, wiring system, shaft, and connector cable. This is the block diagram of a controller, or a way to move a catheter. The power supply from the main system gives power to the controller system, and also every components are controlled by the main system's microcontroller, which is Raspberry Pi 4. Starting with a joystick, a physician can use this joystick to control the movement of the catheter. The catheter is able to move because of 4 pull wires within the shaft of the catheter. There are 4 pull wires, so the catheter can bend in 4 directions. Each pull wire is connected with a stepper motor here. Stepper on line lemma 8. The stepper motor creates tension within the pull wires, and the catheter will bend according to the size of the pull wires that are located on. Then, the load cell functions to give a feedback control. It monitors force within the pull wires. The data from the load cell will be amplified and converted to digital before being analyzed in the microcontroller. Next, the tip.
The tip design is a petal shape with 4 spines and 16 bidirectional microreactors. The alignment pattern of the erector provides the ability to map from any direction with better performance compared to other designs. For the spine, the 255 French gauge spine is made of the nitrile due to its high elasticity and biocompatibility, coated with epoxy for surface protection and electric insulation. Each spine contains 4 microreactors as shown in the picture. For the sensing part, there are microreactors on the spine, electromagnetic coil, and electrode for localization system located in the shaft, as shown in the picture. The microelectrode is a ring shaft made of platinum iridium alloy. It is used to measure intracardiac electrogram from the heart. For localization, the ring electrode is made of the same material as microelectrode to send the voltage for the impedance-based system. And the electromagnetic coil is a copper solenoid coil, works with the Pana coil. The further mechanism of these two sensors will be explained in the localization part. And next is the wiring system.
Next, the wiring system we use ASIC at the end of each spine to digitize and encode intracardiac electrogram or IEGM from electrode to the external receiver or image processing. Components of ASIC. Firstly, multiplexer. Multiplexer receive IEGM around 30 to 500 Hz from electrode. They are sampled at 1 kHz, follow channel sampling theorem. Then, analog front end will filter all the signal by having a notch filter at 50 Hz, a high pass filter at 30 Hz, and a low pass filter at 500 Hz. Then will convert analog signal into digital signal by using analog to digital converter, then compress the data. And because IEGM signal come from different locations in the heart, so we want to make it more accurate, so we use reconfigurable CS encoder. Next, first in and first out, store the data with unknown address and arrange the memory in a queue by the oldest come first and transfer to the a register map. A register map will tell which electrode is read and transfer information to the SPI. SPI or serial peripheral interface will transfer digital data to the external receiver or image processing to create the image. Next part.
For the shaft and connector cable, the 7.5 fin gauge shaft, which is the pathway of the wires with 100 cm length, consists of 3 layers, which are the outer jacket made of nylon 12 because of its insulation properties and its physical properties. The stainless steel braid provides a reinforcement of the shaft. The inner layer is a thin poly thread-top fluoroethylene or PTFE with low electrical conductivity. Additionally, the connector cable provides the connection to the main system by the controller plug-in. And next is the ablation system.
Right, so let's move on to the very heart of the system. Some may call the ablation system as the very point of the cardiac mapping system, by which we would cover the main ablation system itself and its catheter design as well. So let's get started. So first, what is ablation? Ablation is the process of removing the scarring an area of tissue that is causing the problem for the conduction of electricity and otherwise, which in our case is the heart. There are many types of ablations, cryoablation, laser-based, but in our case, our system would utilize the design of radiofrequency ablation. This is chosen since it is the most cost-effective method and just as effective as other methods as well, based on price. So for the design of the system, the heart of the system would lie on the RF generator block, marked number 2 on Roman numerals, and the control board, marked 3 in Roman numerals, by which the RF generator would be generating the radio frequency power based on a dictation of the control board, by feeding the control board with current, voltage, and temperature samples, by which the control board would feed the appropriate power setting back into the RF generator. The control board itself is directly connected to the main processing unit of the whole cardiac mapping system, which is the Raspberry Pi 4, which in turn would be controlled by an operator through the user interface block. The irrigation pump of the system is also connected to the ablation catheter as well and dictated by the Raspberry Pi for an appropriate setting of the saline flow as well. Now for the big part. It all began on a stable oscillator chip, which would be generating the required radio frequency for ablation. This is fed through the non-overlapping clock. This is done to prevent the square wave of the oscillator to turning into become a trapezoidal wave. The voltage driver would then be applied to drive the signal with enough current. This is then fed into the frequency inverter. Note that the center tap of this is controlled by the power control board. This is done so that the system can be controlled and adjust accordingly. The two peak detectors, one for voltage and one for current, is the one that is sending the sampling data back into the control board. Now, explanation in details are mentioned in the report, and if you have any questions, please feel free to mention in the comments, and I'll do my best to answer them. Now, we can see the numerous Butterworth filters here. So let's start with the number E, the letter E first. The letter E on the lower left one is responsible for preventing the voltage return from the frequency inverters, whereas the right center one, if this on the letter F, is for converting the square wave into pure sinusoidal wave that's to be sent to the patient, whereas the one associated with the both of the peak detectors are simply low-pass filters to cut off the excessive noise of the RF generator. Now, moving on to the control board. Now, the power control board would take the input current, temperature, and voltage of the RF block, and it would be controlling the center tap of the RF generation system as well. This is done by using an adjustable voltage regulator by which it would then be passed through the power transistors as to enable the signal to contain enough current to drive the ablation circuit. Now, because of this, we would need a fail-safe system as well. This is done by a fuse, so that if the current are over the limits, the system would just shut itself down and would not damage other components as well. Now, for the relay part, we would be using a solid-state relay since the system is associated with high frequency and that mechanical relay might interfere with it. This would be then controlled by Raspberry Pi, which is then sent to the RF generator block. Right, so moving on to the last topic. This is going to be the catheter design. So for ablation, we will be using a shape memory alloy base system, which would be multiple tendons of these materials to move the catheters around. Now, this is done since by using multiple tendons, the catheter would have superior control and maneuverability. Note that this is also the only difference from the mapping catheter as well, where the rest of the components are completely identical with one another. The catheter would also feature an open irrigation system, which would have 6 cavities for dispersing saline flow. This is done to help cool the heart's tissue during ablation, eliminating the danger of steam pops and thrombus formation. Next, we'll talk about pressure sensors.
As the pressure can also affect to the lesion size resulting from ablation process in our design, we hence include the precision spring to calculate the force, which it will work cooperatively with the localization system, and the principle behind this design is based on Hooke's law. And for next part, it will be the localization system. There are several localization processes to navigate the catheter during the operation, and there are 4 main types for navigation method: MRI, which stands for magnetic resonance imaging; fluoroscopic, the method that we use the X-ray to locate the catheter; EMT, or electromagnetic localization. It is a method that we use the induced voltage generated from the movement of the catheter under the electromagnetic field. And last but not least, impedance-based localization, which is the method using of the current detected from the 6 patches attaching on the torso surface of the body by 3 at the front and the other 3 at the back. And for our research, we propose the method using 2 navigation systems, which is electromagnetic and impedance-based localization, as them both have cost-effective and they can work compatible with each other, which may reduce the error from each system. So let's get more detail. Let's start with the first one, electromagnetic localization. Based on Faraday law, when we move a coil sensor under the magnetic field, the voltage will be induced, detected, and transferred to data acquisition for sampling, and it will be used to localize the catheter. But there's still some disadvantage for this method as well, which is the position of the prana coils and the generated The position of prana coils that are generating the electromagnetic fields must be precise as much as possible. Thus, when the patient moves during the surgery, the operators must adjust the position of the patient again, which is inconvenient for both operators and the patient himself. And here is the block diagram for our system. The specific frequency is generated by AD9833. Then the generated current will be directed to TLO82 and PID controller for producing a phi current. After the current is amplified, it's being sent to prana coil, which will be detected by solenoid coil, and then the voltage caused from the electromagnetic field will be sent to algorithm for localize the catheter. And for the next one, impedance-based localization. The method used for navigating the position by using the fundamental principle, Ohm's law. When the constant voltage applied to the ring electrode on the catheter, the patches which we attach on the surface of the body with ground supply voltage will detect the current, which will inversely proportional to the resistance. Then we can use the acquired current to calculate the position of the catheter. However, the disadvantage for this method is the difference in impedance in each person, which is come from the tissue or compound of the patient himself. And here is the block diagram for impedance system. The ring electrode is on the catheter, distributing a constant voltage. Then the current will be detected at the patches by using PAC 194X2. The detected current will be used for navigation of the catheter. And this is the EKG signal sensor that we use in our system.
In the external part, we just to make sure that EKG signal of patient is still good, so we use IC AD8232 with microcontroller to extract EKG signal. And the next one is overall international organization for standardization that we should follow to create this machine. And thank you for your attention. This is overall for our group.